So in a typical function, we want a docstring and other things. But this time, let's just see what we're looking at. What do we want to return? Well, we need the absolute value of x. And how do we raise that to the p power? And then what do we want? We want the absolute value of y. And then we want to raise that to the 1 over p power. So, like this? Yeah, we better put parentheses around it, because what happens if we don't put parentheses around it? What have we really done? We'll raise it to the first power and then divide by p. Right? But we want to actually raise it to the 1 over p power. And that's all we need to do. Right? This will then give us a correct value, hopefully. What happens if we do the 1 norm in this case? The 1 norm, that would mean norm 2, comma, negative 3, comma, 1. And what should it give us? What does it give us, though? Probably not. Give me 5.0, right? Because it makes a change. Even though it was all integers, it makes a change because of raising those things to, well, actually, the 1 over p root. That method causes it to become a float. All right, so again, it's 5, but Python's going to call it 5.0. All right, so what does that mean? That would mean you've gone 2 that direction and 3 in the negative y direction in that particular case. All right, what is the 2 norm for this? What is it?
The decimal form is like 3.6.
Okay. All right, it's square root of 13, which is about 3.6 something, right? Which is what we expect that to be. All right, now there's another norm. We could do 3 norm, 4 norm. We could do all these, but there's another one in particular that has meaning. So P1 or 2, they have meaning. We've already seen what that is. There's another norm called the infinity norm. Sometimes it's just written like this. Sometimes it's called the Chebyshev norm, named after, again, obviously a person with that name. And the idea is it's exactly the same as all of this, except we're imagining what would happen but we can't put infinities in there because those aren't actual numbers, right? So it's not that. It's not really putting infinity in there. But we can mimic what happens by putting in big numbers. All right, so let's try this again. Run this with the same A. But this time, let's try P equals 10. What happens when you run this with P equals 10? Right, it's 3.0 something, right? Let's try P equals 20.
Are we basically finding the limit of this?
Yeah, it is a so yes, the infinity norm is finding the limit as P gets bigger and bigger. So if you've had calculus, we're looking at the limit as P approaches infinity. So what happens when you put P equals 20? Even closer to, let's try P equals 100. Just gives us back 3.0, right? All right, so let's do this. Let's try different values for x, whatever vector you want to use for the x and y values, and leave p at 100 and see what you get back from this method. You can put positive numbers, negative numbers, whatever you want into your vector. So what vector did you put in?
I just keep typing something. When I put 20, negative 13.
You put 20, negative 13? And it gave you?
20.2.
What did you put in?
18 and 16.
18 and 16? And it gave you? 18. Put like 700 and negative 300.
Almost completely something.
All right. Gives us, maybe not quite, but it gives really close to 700. If we made the p a little bit bigger, it would. All right, so what happens? What does this infinity norm give us? Actually, the absolute value, we should have had one with a negative. It gives us the biggest absolute value. Is there ever a time when we would need a distance based on the biggest absolute value? Let's say we had a chess piece right here, and we're trying to get to there. So if we had a rook, how far is it for a rook to get from here to there? Well, what is a rook? How can a rook move? Up, down, left, and right. So what's it going to take in terms of distance to get there? So it can get there in 2 moves, but how far is it? Well, it would have to come over this far and then up that far, right? So what would its distance be? 1, 2, 3, 4, 5, 6. The distance would be 7. What if we made that in a different set of moves? We could do that like this. How far did it still go? Still went 7. So what kind of distance is this? Well, a rook has to stay on the grid lines. Right? It has to stay on the grid. So what is this? This corresponds to a 1 norm in terms of the actual distance for the rook to get from here to here. Now, not how many moves, right? That's a different question. But how far is it? All right, what if we looked at a king instead? What could the king do? The king can move 1 unit in any direction, right? So what could the king do to get to here? The king could say 1, 2, 3, 4, 5. Or a different way, right? The king could get there in different ways as well. What if the king chose a different way? Give me another route for the king to take. Which way do I go? Up, right, or diagonal? Diagonal. Or diagonal? Diagonal again. So we've gone 2, 3, 4, still 5. All right, so let's think about this. How far does the king have to go left and right, left to right? The king needs to go a total distance of 2 left or right. How far up does the king need to go? The king needs to go up a distance of 5. Well, what can the king do? The king can take care of the 2 at the same time as doing part of the 5. But there's nothing the king can do to avoid going up a distance of 5. Make sense? So the king can take longer to get there, but when we talk about distance, we're talking about the shortest way to get there, or a shortest way. And so this king doesn't want to go all the way over here and then all the way up, because the king can take care of this. The king took care of that part here and here while still going up, and took care of it on this one here and here going up along the way. And so what happens? For the king, the distance is 5. And what does that correspond to? Well, a straight vector from here to here is 2, 5. But the king doesn't measure distance, and the rook, they don't measure distance in straight lines. They measure distance. The rook has to stay on the grids, and the king can move from square to square by staying on, well, the allowable squares, right? So it's horizontal, vertical, or diagonal. And so the king's distance is 5. So what happens for this? This is a use of the infinity norm, right? This is a use of the 1 norm. So what's going to happen? Depending on how a character can move, its distance might be given in different ways. Right? How far has it traveled? How far does it have to travel to get from one place to the other? It might be an infinity norm. Now, that means that we're going to look at 1, 2, and infinity norms, and we're not really going to deal with anything else. Some of those have uses, other p-values, but for our purposes, it will mostly be these 3, and it will depend. Most of the time, it'll be 2 norms. It's normal distance that we care about. But there will be lots of times when we have to stay on a grid, or we can stay on a grid, but it's not just a rectangular grid. It's a grid that has connections like this as well. So if we have all of these kind of connections, then the infinity norm might be a better way of measuring distance. Okay? So we're going to incorporate different norms, a method rather than a function in our lab. Not lab 5. This will be part of the follow-up for vectors. We're going to add a lot more components to the vector lab. So what we're going to do now is, well, first of all, are there any questions? As usual, if you have any questions, Discord or email if you don't want to ask in person. And otherwise, we can do some practice, do some work. So what we'll do